Hello students, next let us look at the Fourier transform of the Signum function. We all know that the Signum function can be drawn as this, which is defined as Signum function with respect to t is basically two values, one for t greater than 0 and minus 1 for t less than 0. Now again, as you can see that if I try to take the area under this curve, it will come as not integrable. But what we can do generally is we can find out the Fourier transform of the Signum function by considering another function, which I will draw it like this, where I can define this function as basically e raised to power minus at at u of t plus at the other side it is going to be minus, so I will put it as minus e raised to power, since it's negative t I will have to write e raised to power at u of t. This is this function which I will now write it as some, let's say some y of t. Okay, and this function I can make it as a Signum function by basically reducing the decay. See here the decay is basically given by e raised to power minus at, correct? So here a decides what is the decay rate. A decides what is the decay rate. If a is equal to 0, then the decay rate is actually 0. That means it won't decay. Then it will represent close to Signum function. So it means that I can say that Signum function can be written as, therefore Signum function can be written as e raised to power minus at u of t minus e raised to power at u of minus t. Did I write u of minus t here? Sorry, here it should be u of minus t. Yeah. So it is basically this, but with the decay rate to be 0 or decay rate to be approaching 0, which I can write it as limit a tending towards 0. A tending towards 0. So this is my Signum function, and now based on this I can try to find out the Fourier transform. So I will write therefore the ft, the Fourier transform will be, we know the equation of Fourier transform, it is x of omega is equal to integral minus infinity to infinity x of t e raised to power minus j omega t dt, where I am going to substitute this equation. So therefore I will get x of omega is equal to minus infinity to infinity. Instead of x of t I will write limit a tending towards 0, then e raised to power minus at u of t minus e raised to power at u of minus t multiplied with e raised to power minus j omega t dt. Okay, where now I can take the limit outside and I will take the integration inside. So I will write therefore x of omega is equal to the limit I will take outside, limit a tending towards 0, and then within brackets I will write that I will take the integral for both the cases. So minus infinity to infinity e raised to power minus at u of t, correct? U of t means it's as good as writing the integral from 0 to infinity. Therefore, now I will avoid u of t. So u of t is avoided into e raised to power minus j omega t dt. And for the second case, again integral e raised to power at u of minus t. U of minus t basically exists from minus infinity to 0. So from minus infinity to infinity, that has changed from minus infinity to 0. E raised to power at e raised to power minus j omega t dt, bracket closed, which now I can again change it as x of omega is equal to limit a tending towards 0, and these two I can join as 0 to infinity e raised to power minus a plus j omega t dt minus minus infinity to 0 e raised to power a minus j omega of t dt, from which I can get, therefore x of omega is equal to limit a tending towards 0, this I will keep like this, and now the integration is going to be e raised to power minus a plus j omega of t divided by minus of a plus j omega with limit 0 and infinity minus, then here we are having e raised to power a minus j omega of t divided by a minus j omega. The limit is basically from minus infinity to 0, and then bracket closed, which you can directly see. If I am going to apply the limit, then I will get x of omega is equal to limit a tending towards to 0, and now here e raised to power minus infinity is 0, 0 minus e raised to power 0 is 1, so I will get minus 1, that minus 1 and the denominator minus of a plus j omega, that minus and minus will cancel, so I will basically write this as 1 divided by a plus j omega minus, here if I put 0, so e0 is equal to 1, 1 minus 0, so this is going to be 1 divided by a minus j omega, correct, which can now be simply written as limit a tending towards 0, and now we are having the x minus y into x plus y scenario, so it is going to be x square, which is a square minus of j omega square, so j square will be another minus, so this will be plus omega square, and then in the numerator I will have a minus j omega, a minus j omega minus of a minus of j omega, from which you can see that minus a and a will cancel, and only one minus 2j omega will remain. So I will straight away write that, I will not waste any more lines for that. So minus 2j omega. Okay, now if that is the case, then this can be basically written as, if I am going to apply the limit a tending towards 0, then I will get minus 2j omega, and 1 omega will cancel in the denominator, so I will get 2j omega minus 2j omega, or I can write it as 2 by j omega. So I can write finally that the Signum function of t, the Fourier transform of that will be 2 by j omega, where the magnitude of x of omega is going to be basically 2 by omega, and the angle is going to be, it's minus j, or j is in the denominator, so minus j is pi by 2, so angle of x of omega will be minus j, that is minus pi by 2 for, so I will write minus pi by 2 for omega greater than 0 and pi by 2 for omega less than 0. Now let me plot this in a new page. So magnitude wise it is 2 by omega. So you can see when I write 2 by omega, when omega is equal to 0, this will become 2 by 0 is going to be infinity. If omega is equal to infinity, this will basically go to 0. So we can basically draw this. You can look at the different values. It will never touch this axis, neither it will touch this axis. It will touch these axes only at infinity. Similarly, when omega is equal to minus, when omega is equal to minus, it is going to have similar values, and where this is basically 0, so at 0 it is infinity, so we cannot show. Similarly, for x omega we will get negative pi by 2 for positive omega axis and positive pi by 2 for negative omega axis. So this is going to be pi by 2, this is going to be minus pi by 2. So this is the spectrum, the frequency spectrum of a Signum function. Next, let us look for the case of a unit step function. Now unit step function, we use a particular trick. The trick is basically, suppose if we are going to have a function, if I am going to just draw a Signum function. Okay, let me draw the Signum function. We all know that the Signum function is basically drawn like this, correct? Now the unit step function basically talks only of this part, whereas this part it is always going to be 0. So here it is suppose minus a, or let's say minus 1. Here it is minus 1. This is plus 1. So to make this one u of t, I have to basically make this side as 0. So for doing that, so this is Signum function. So what I do is I write Signum function plus 1. So if I add everything 1 with the Signum function, then here minus 1 and 1 will basically become 0. That is true. Whereas what will happen in this side, positive side, is 1 plus 1 will become 2. So I will have a value at 2. So but unit step is having the value at 1, not as 2. So I will just divide this whole value with 2. So now this can be written as the unit step function. U of t is basically Signum function plus 1 the whole divided by 2. So what I will do is I will write, we can write unit step function u of t is equal to this equation, which is Signum function plus 1 the whole divided by 2. Or basically I can write 1 by 2 times of Signum function plus 1 by 2. Okay, therefore the Fourier transform of u of t is basically the Fourier transform of half times Signum function of t plus the Fourier transform of, I should write the Fourier transform of 1 by 2. The Fourier transform of 1 by 2. See, already for the case of Signum function we have got the, we know Fourier transform of Signum function. Just now we wrote it is 2 by j omega, 2 by j omega. Therefore the Fourier transform of half times Signum function is going to be half times 2 by j omega, which will become 1 by j omega. You might be thinking, where is this property coming from? This property we will learn later, but anyway, you know that if you multiply, and you know the property of linearity is basically being used here. But anyway, you have already studied linearity property in Fourier series. The same thing will come here. The Fourier transform properties we will see next. But anyway, so this is the case. Similarly, so and I will write, and f of a, we have already seen that if you have any function a, constant value a, then its Fourier transform is 2 pi a delta omega. Therefore, I can write that the Fourier transform of 1 by 2, so instead of a it is 1 by 2, so I will get pi delta omega. Clear? Therefore, we can conclude that the Fourier transform of the unit step function u of t is going to be the first one, which is 1 by j omega. Let me write it properly. 1 by j omega plus pi delta omega. Let us plot this. So for plotting, I can write u of t, this 1 plus j omega, and then for the magnitude of x of omega, the magnitude we will have two portions. One is 1 by j omega and another is a impulse function at omega is equal to 0 with amplitude of pi. So both of them I can draw it as, this is 1 by j omega, it will not touch the axis. Similarly, this one also 1 by j omega, and then the impulse function in the center, this one. So this is going to be the magnitude of x of omega. Similarly, the phase angle of this one, x of omega, phase angle of x of omega. As you can see here, the phase angle will be what we have seen previously, that is the one that we saw here, this one. Whereas for the second portion, for the second part, that means for this one, the phase angle is 0. So it is as good as redrawing this one itself at pi by 2 and minus pi by 2. So we will draw it as pi by 2 and at minus pi by 2. So pi by 2 and at minus pi by 2. Next we will see for the case of a rectangular pulse. Another important function is a rectangular pulse. The rectangular pulse is as shown here, which we write it as rect t by tau. It has two values, 1 and 0. 1 is for the time period t less than tau by 2 and greater than or equal to minus tau by 2, and 0 elsewhere. Now for this, let us find out the Fourier transform. We already know the equation of Fourier transform x of omega is equal to minus infinity to infinity x of t e raised to power minus j omega t dt, where the x of t is equal to 1 at the limit minus tau by 2 to tau by 2. So outside that limit it is 0, so there is no point in writing the limit outside that. So inside that it is equal to 1 into e raised to power minus j omega t dt, which we can directly solve it. X of omega, the integration will be basically e raised to power minus j omega t divided by minus j omega with the limit tau by 2 and minus tau by 2, which comes out to be e raised to power minus j omega tau by 2 minus of e raised to power minus j omega minus tau by 2. So that minus and this minus becomes plus. So what remains is tau by 2 divided by minus j omega. We know the Euler's function or the Euler's function as it is said. It basically is e raised to power minus j theta, which I can write it as e raised to power omega tau by 2 minus e raised to power j omega tau by 2, correct, divided by j omega. So if I am going to take the minus on top, then this will become minus and this will become plus. So it's as good as writing this one as first. So this I will write first, then I will write this. So I will write this as, sorry, so this I will write it as plus e raised to power j omega tau by 2 minus e raised to power minus j omega tau by 2 divided by j omega. And we know Euler's function is basically sine theta is equal to e raised to power minus e raised to power plus j theta minus e raised to power minus j theta divided by 2j, correct? It is divided by 2j. So if I want to take 2j at the, if I want to take 2j at the denominator, then here I will have to first cancel out omega, and then I will have to put here 2. So what I will do is I will write x of omega is equal to take out that omega, I will multiply this with omega, okay, so that it cancels out. So when I am multiplying, I have to divide it also with omega, correct? And then I will have to multiply it with 2 and also divide it with 2, okay? Then multiplying the remaining portion, I will multiply e raised to power j omega tau by 2 minus e raised to power minus j omega tau by 2 divided by j omega. So j omega I will write this omega, and omega will basically cancel out, omega basically comes out. This 2 is going to be here. So in a way I can basically write this as 2 by omega, okay? So I can write this as 2 by omega. The omega has got cancelled, so this is what remains with another 2 here, 2j, where the what is inside the bracket can be written as sine, okay? So this can be written as 2 by omega sine theta. Theta is what here? Omega tau by 2. Now if I want to bring it the denominator, if I want to bring a tau by 2, sorry, omega tau by 2, omega directly I am getting from here, so no need to bring an omega. Omega I have already got in the denominator. And then tau by 2, if I have to bring, I have to multiply it with tau by 2. So I will basically multiply and divide with tau by 2. Now you might be considering, or you might be thinking, why am I doing that? Why am I multiplying and dividing with tau by 2? What is the need for multiplying and dividing with tau by 2? Because there is some function which is called as a Sinc function. I will explain it very shortly. So omega tau by 2. Now here if you would see this omega tau by 2 in the denominator can be written together as a denominator of sine function. So what will remain is this 2 and tau by 2's 2 will get basically cancelled, and what will get only as a tau into sine omega tau by 2 divided by omega tau by 2. And generally there is a function which is called as a Sinc function, which is sine x divided by x is called as a Sinc function, okay? So here we have got the sine x, this can be taken as an x, this is also x, so this has come now in the form of sine x by x. That is why I basically wanted to introduce a tau by 2 at the denominator here. So once I have done that, I can write this as tau sinc function of omega tau by 2. And sinc function, we have already studied what is sinc function. So therefore, I can say, finally, I will write it. The function that we had started with was rect. So rectangular pulse of function of t by tau, the Fourier transform of that will be tau sinc omega tau by 2. Now the magnitude and the phase part we have to draw. The magnitude of the same can be drawn like this. So this is the sinc function. You can see that there is a slow decay of the sinusoidal signal. There is a slow decay. That is because the sine function has sine x divided by x. So as the value of x keeps on increasing, the sine function will go like this. But the x function, as it is increasing, the value of the total will basically reduce. That is what is basically shown here, that it is basically reducing. Now, the main thing to see here is where are the zeros occurring. The zeros are occurring at the tau we know. So the zero is occurring at 2 pi by tau, where this tau is basically coming from here. So 2 pi by tau, 4 pi by tau, 6 pi by tau, 8 pi by tau. These are the frequencies, omega values at which the values are occurring at 0, even here. About 0, if you take omega is equal to 0, so what will you have? So sine omega is 0, that is 0, divided by omega tau, again it will be 0. So sine 0 is 0. So 0 by 0, we know that it is not possible. So the sinc function, this already I have done when we had discussed sinc function. So sinc at 0 will be basically found out by differentiating with respect to omega the numerator, which is sine omega tau by 2, divided by the differentiation of with respect to omega of omega tau by 2. And we know that the differentiation of the sinusoidal will be cos, so it will be tau by 2 cos omega tau by 2 divided by tau by 2, but tau by 2 basically cancels off, and we have to find out this value at omega is equal to 0. So this one at omega is equal to 0, we will get the value as cos of 0 is equal to 1. So that 1 will come here, but since that 1 should come here, but since here it is multiplied with tau, I will write this maximum amplitude to be tau. So the maximum amplitude is tau. The first 0 occurs at 2 pi by tau, like that. Similarly, if you would look at the phase angle will be just like what we have drawn here. The phase angle will be similarly drawn as. So as you can see here, we will have the values of the multiples of omega in such a way that from 2 pi by tau to 4 pi by tau it will be some negative phase, and similarly in the negative axis it will be all positive phase. So this is the phase diagram of the sinc pulse. You might be thinking, where did we get this phase from? You can basically get the phase from this equation. Okay, you can basically get the phase from this equation. But anyway, this is the phase that we have got. I should mention that it will be here, it will be minus pi, and this side it will be plus pi. So this is minus pi and this will be plus pi. Now you might be also asking, how did we get these zeros here? See, sine of omega tau by 2 by omega tau by 2. So now forget about the denominator. This sine function is what brings the zeros, and we know that sine functions bring zeros whenever the multiple of this is some multiple of pi. So let us say that it is some multiple of plus minus n pi. Which one? Whenever omega tau by 2. So I will say that omega tau by 2, whenever it is some plus minus n pi, I will get the values as zeros. Which one? The Sinc function will give me zeros. That means at these values. So how did we get that? From this you can get omega is equal to plus minus n pi into 2. So 2n pi divided by tau. 2n pi divided by tau. Now if you keep on putting the value of n is equal to 1 onwards, so we will get 1, this 2 pi by tau, then 4 pi by tau, 6 pi by tau, similarly in the negative axis.